Hi everyone, I will talk about the method of Lagrangian descriptors and its connection to an assertive quantification method. This talk is split into two parts. In the first one, that is theoretical, I will present the main ideas, like what is a phase space, the method of Lagrangian descriptors, and then in the second part, I will present one example. In general, I will present also a new assertive quantification measure appropriate for quantifying the performance of models in assessing, for example, the origin or source of a given observation. And we have noticed that in the neighborhood of the observation, this assertive measure is related to the dynamical, invariant dynamical structures of the model, such as hyperbolic trajectories and their stable and unstable manifolds. So I will present basically the method of Lagrangian descriptors, as I said before, that is a qualitative method, and the assertive quantification method, that is a quantitative method. So the phase space. Phase space structures are a geometrical way to look into the solutions of system of differential equations. And this idea about this geometrical way to look into the solutions was introduced first by Poincaré in the context of celestial mechanics. And given that dynamical systems have many applications in many areas, these ideas of Poincaré have a lot of impact in many areas. And this idea looking into the phase space allows in a geometrical perspective to have an intuition just with a glance on how the phase space is divided into regions where trajectories have different qualitative behaviors. And as I mentioned before, these ideas have an impact in many areas. And I will explain in this talk how these ideas can explain transport in the ocean. So the method of Lagrangian descriptors is a scalar trajectory diagnostic that is similar to other chaos indicators, such as Lyapunov exponents, for example. And the method of Lagrangian descriptors has the capability of revealing the invariant manifolds in phase space that characterize the system dynamics. So this method can reveal stable and unstable manifolds. It can also reveal KM tori. And the development of Lagrangian descriptors was originally inspired by the desire to explain the geometrical patterns that govern transport in geophysical flows. Then the method of Lagrangian descriptors is based on a function M, as you can see here, that is a scalar function that we obtain by integrating forwards and backwards in time in a three-dimensional space for initial conditions. And this function has been presented in two papers, one from Madrid and Mancho in the journal Chaos in 2009, and in the paper by Mendoza and Mancho in Physical Review Letters in 2010. But what is exactly the method of Lagrangian descriptors? It is a very simple technique to use, and it works in the following way. So imagine that we want to reveal phase space structure in a given slice. So we choose a slice and we define this slice a grid of initial conditions. And then what we do with these initial conditions is that we integrate these forwards and backwards in time for a given time tau. And while we are integrating, we accumulate along these trajectories a positive quantity defined from the vector field that determines the dynamical system that we are studying. So in the original definition of Lagrangian descriptors, they are calculated by accumulating the arc length of the trajectories. So we know that if we integrate trajectories forwards, the LD function, that is a scalar function, and it's going to detect for you the stable manifolds, while if you do the computation only backwards in time, it will detect for you the unstable manifolds. So how are these manifolds revealed by the method? So the location of these stable and unstable manifolds are revealed in the scalar field at locations where the values of the scalar field changes very sharply. So in these regions, the gradient of the scalar field presents very large values, and tau is the parameter that we have to fix in order to integrate trajectories for different time intervals. So the example I will present is a joint work with Stephen Wakings from the University of Bristol in the UK, Ana Maria Mancho from ICMAT from Spain, and Guillermo Garcia Sanchez, that he is the CTO of Digital Earth Solutions. So this example, the purpose of this example that it has been published in Physica di Nonlinear Phenomena was to propose a new assertive measure appropriate for quantifying the performance of transport models in assessing the origin or source of a given observation. And we found that in the neighborhood of the observation, the proposed assertive measure is related to the environment, dynamical structures of the model. And what we did also was we illustrate the implementation of the proposed definition to quantify the performance of ocean data sets in the context of a real oil spill event that happened in the Mediterranean, in the Eastern Mediterranean in 2021. And we were interested in assessing models that provide information about when and where did the spill originated. So what happened is that at the beginning of 2021, the coastline of several Middle Eastern countries in the Eastern Mediterranean was affected by the presence of oil from unknown sources, and no accident were reported for these spills previous to their arrival at the coast, and therefore was no hint of their origin. So the first time that the method of Lagrangian assertive quantification was presented was by my colleagues a year before our publication in this paper. And just for the sake of completeness, I'm presenting here the definition that we use in this paper for the Lagrangian backwards assertive quantification. You can see here that with x1 capital is the neighborhood of the observation, that is x1 small, at time t1, and of course we care about 2 dimensions, and then the coordinates of the target are x1 asterisk, x2 asterisk. Remember that our target, it is backwards in time. So here in this figure, we illustrate some affected geographical areas. So for example, you can see the orange and green colors along the coastline mark the olive arrivals, and then the systematic search of satellite images identifying potential sources of these observations. And a careful examination concluded that those sources are owned by green and orange polygons, which correspond to satellite observations, were located in position and time in a manner consistent with the position and dates of the oil that arrived at the coast. And then these orange polygons labeled as A and B are successive earlier locations to the orange arrival labeled as C. And then these green polygons labeled as D and E correspond to the green arrival labeled as F. And you can see the dates and everything here. So the spill was closely following fluid partial trajectories that obey specific equation that is a nonlinear autonomous, non-autonomous dynamical system in 2 dimensions. And it is required for implementing the backward evolution of fluid partials in the previous expression. And then Lagrangian assertive quantification backwards in time will have different evaluations for different CMEMS datasets, right? And the goal of this paper is to use these outputs to discriminate models because CMEMS, for example, provides 2 datasets describing currents in the Mediterranean Sea, that is the global product and the Mediterranean product. And given that both models provide information for the same area, a natural question is to determine whether one is more suitable than the other for describing transport in the type of event described above. So dynamical models, such as the one that I talked about before, possesses a transport signature based on invariant manifolds associated with hyperbolic trajectories, which, following Poincaré's idea, constitute geometrical structures on the ocean surface that organize particles schematically by regions corresponding to qualitative different types of trajectories. And these geometrical features allow a more robust analysis of the transport capacity of ocean currents than that based on individual trajectories. So in the context of geophysical flows, these geometrical structures are referred to as Lagrangian coherent structures. And the use of these Lagrangian coherent structures allows a qualitative assessment of the performance of datasets. However, definition sets, as the one given in the question before, allow a quantitative analysis that we will implement next in the context of the oil spill event that I mentioned. And we compute the Lagrangian coherent structures using the method of Lagrangian descriptors, where the integral in the M function evaluates the arc length of the trajectories on the latitude-longitude plane at the ocean surface. So here, what we can see is, remember, here in this coastline, the target backwards in time was this polygon D. So considering this origin, this target, we calculated the Lagrangian character quantification backwards in time. It is what you can see in this first column, and the Lagrangian descriptors backwards in time, that's what you can see in the second column. And then the first line, you can see the result, the outcome for both methods using the first data set, that is a global model. And then in the second line, it is the result using the second data set, that is the Mediterranean model. So we have several conclusions. For example, which data set is performing better. Here we can see we are interested around the area of this coast. So we can see that the error around this area using the first data set, it is smaller than this one here. And then the other conclusion that we can get is that the invariant manifolds and stable manifolds that we are getting from the method of Lagrangian descriptors are very beautifully aligned with the structures that we are getting, with the singularities that we are getting using the method of Lagrangian character quantification backwards in time. Then we repeat the same process for this coastline, and taking into account that the target backwards in time, it is what it is inside this polygon labeled as A. So again, first column is the Lagrangian character quantification backwards in time, and then second column is the Lagrangian descriptor, and then the first line we have used the data set of the global model, and the second one the Mediterranean one. So again, we can see that the global model is performing better. The error around this area is much smaller than using the Mediterranean model, and again, the invariant unstable manifolds are very aligned with the singularities that we are getting using the uncertainty quantification method backwards in time. And then we were thinking that what if, instead of considering the targets, like for example, what happened in this coastline C, instead of considering as a target the area A, we consider the area B, that basically it is where the oil spill was transferred after a few days. And then instead of considering as a target of what happened to this area F, instead of the area D, we consider E. So basically considering closer targets. So then we calculate it again. Here in the first column, we use the first data set, the global one, and the second one, we use the Mediterranean data set. And we can see, for example, here, the Mediterranean data set is giving a smaller error, so it's performing very well in this case of the closer targets. So some of the basic conclusions is that the Lagrangian character quantification method backwards in time, the outcome of this method, the structures that we are getting are really linked to the unstable invariant manifolds of the hyperbolic trajectories that we are getting using the method of Lagrangian descriptors. And we saw that using a real event that happened in the Eastern Mediterranean in 2021. Another example, another conclusion important is that which CMEMS product, which data set is performing better. And we saw that if we consider targets that they are further away from the coastline, the global Mediterranean model, the global model, CMEMS model, is performing better than the Mediterranean one. But if we consider closer targets to the coastline, then the Mediterranean product performs quite well as well. So you can find more details in this project, in this paper that it has published in Physica D. And then if you have more questions or you want to collaborate, you can email me in this email address. Thank you very much.